There's a crater on the moon that hasn't seen sunlight in over 3 billion years. Not a flicker. Not a glint off a crater wall. Nothing. The interior sits permanently at around -183 degrees Celsius, and on the floor itself, it drops even further, down to -185. That's colder than liquid nitrogen. Colder than most of the surface of Pluto. Whatever landed inside that crater when the solar system was still young is still there, perfectly preserved in permanent dark, undisturbed for longer than complex life has existed on this planet. Scientists first started seriously thinking about this in 1961. Three astronomers, Kenneth Watson, Bruce Murray, and Hugh Brown, published a paper in a journal called Icarus, arguing that permanently shadowed polar craters on the moon could act as cold traps. The temperature would be so extreme, they said, that anything deposited there, water ice from comets, volatile compounds from the moon's own ancient geological activity, would simply never leave. The physics wouldn't allow it. At those temperatures, the estimated rate of ice loss from the interior would be so close to zero that it's essentially meaningless to calculate. The ice just stays. Forever. That paper sat on the edge of mainstream science for decades. A curiosity, a hypothesis. And then in the 1990s, a spacecraft called Clementine flew over the lunar South Pole and bounced radar signals off the interior of this particular crater and picked up a reflection that didn't match bare rock. Something down there was behaving like ice. The scientific community argued about it immediately because that's what scientists do. Some said the reflection was from rocks, not water. Others said no, that specific radar signature points to something frozen. The crater is called Shackleton. It sits exactly at the moon's south pole, coordinates 89.67 degrees south, which means its center is barely a fraction of a degree away from the pole itself. It formed about 3.6 billion years ago, making it older than the oldest complex life on Earth. It is 21 kilometers wide and 4.2 kilometers deep. The moon's axial tilt is so slight, only 1.5 degrees, that the sun's angle never ever reaches the interior. The rim of the crater gets near constant sunlight because of the geometry of how the poles face the sun. But the inside stays dark. Always. And right now, in 2026, two of the most powerful nations on Earth have active missions pointed directly at it. The reason both programs are converging on Shackleton, the reason $30 billion is being reorganized around one geological feature on the moon, comes down to what's probably sitting at the bottom of it. NASA's Lunar Reconnaissance Orbiter has been circling the moon since 2009, mapping its surface in extraordinary detail. The data it sent back from the South Pole region showed something specific. The reflectivity inside Shackleton crater is anomalously high at certain wavelengths. Neutron detectors picked up hydrogen enrichment in the same area. Ultraviolet instruments detected absorption patterns consistent with water frost. None of these instruments can say definitively that there's ice down there. That would require landing something inside the crater and touching it. But the signals, taken together, have convinced most planetary scientists that something frozen is present. And what scientists think is there is water ice, possibly distributed from the surface down to several meters deep. Now, water on the moon sounds like it's useful mainly in a practical survival sense. Astronauts need to drink, they need oxygen. Fine. But that's almost a secondary consideration. The bigger thing, the thing that makes exploration planners genuinely excited in a way they rarely get, is what happens when you run electricity through water. You split the molecule. Hydrogen and oxygen come apart, both of which happen to be the exact chemical components of rocket propellant. So what's potentially sitting at the bottom of Shackleton isn't just a water source for a lunar base. It's a fuel depot. It's the ability to manufacture rocket propellant on the moon itself, from local resources, without shipping every single kilogram of fuel up from Earth's gravity, well at enormous cost. The crater's rim, meanwhile, gets that near-constant sunlight, which means solar power. Put the base on the rim, you have electricity. Drop a probe into the floor, you potentially have fuel. Together, that combination makes Shackleton not just a scientific target, but the most strategically valuable piece of real estate in the inner solar system right now. Whoever builds infrastructure there first is sitting on both the power source and the fuel source for every mission that wants to go further. That's not a small thing. That's potentially the difference between the moon being a destination and the moon being a launch pad. On December 14, 1972, an astronaut named Gene Cernan climbed the ladder of the lunar module Challenger, looked back at the surface one final time, and became the last human being to stand on the moon. He was the Apollo 17 mission commander. Harrison Schmitt, a geologist, the first and only trained scientist to ever walk on the moon, had already climbed up. They'd spent 75 hours on the surface in a valley called Taurus, Littrow, collected 243 pounds of rock and soil samples, driven a rover across the terrain. Before climbing up, Cernan said, and these were the last words spoken on the lunar surface before departure. America's challenge of today has forged man's destiny of tomorrow, then nothing. For 53 years, no human being set foot on the moon again. Programs were proposed and cancelled. Money was redirected. Political priorities shifted. The Constellation program under the Bush administration aimed at a return by 2020, cancelled in 2010 before it got close. The hardware, the momentum, the national will, all of it repeatedly assembled and then scattered. And then something shifted again, and this time it seems to be actually moving. On April 1, 2026, NASA launched Artemis II, the first crewed mission to the moon's vicinity since Apollo 17. 4 astronauts, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. Their spacecraft, named Integrity, carried them 695,000 miles in total over 10 days. On April 6th, they completed a 7-hour lunar flyby that took them closer to the moon than any humans had been since 1972. They passed within roughly 6,500 kilometers of the surface. The crew photographed craters, ancient lava flows, surface ridges. Christina Koch described what the craters looked like from that distance. She said they looked like a lampshade with tiny pinprick holes, the light shining through, brilliantly bright against everything else. That mission ended with splashdown in the Pacific on April 10th. No landing, no surface contact. But humans had been back near the moon after more than half a century. The same week that crew came home, NASA was also doing something else, something that got far less coverage than the mission itself. For years, most of the last decade, honestly, NASA's plan for getting humans back to the lunar surface involved building a space station in lunar orbit first. It was called the Gateway. The concept made sense on paper. You put a small modular outpost in a near rectilinear halo orbit around the moon, use it as a transfer point, let astronauts move between deep space vehicles and lunar landers there, rest, resupply, then descend. A bridge before the crossing. And they weren't just planning it, they were building it. In May of 2019, a company called Maxar Technologies was awarded approximately $375 million to build the Gateway's power and propulsion element. That's the module that would keep the station in orbit and generate its electricity, the backbone of the whole thing. Northrop Grumman received a contract worth around $935 million for the HALO module, Habitation and Logistics Outpost, the section where astronauts would actually live. SpaceX and its Falcon Heavy rocket were selected in 2021 for a $332 million launch contract to carry these two components to the moon. International partners joined under formal agreements: the European Space Agency, Japan's JAXA, the Canadian Space Agency, the United Arab Emirates, each contributing hardware or funding under a shared expectation that the Gateway was a real program moving toward real hardware. By April of 2025, the HALO module had crossed the Atlantic Ocean. Built by a company called Thales Alenia Space in Turin, Italy, it arrived at Northrop Grumman's facility in Gilbert, Arizona. Engineers were outfitting it, fitting systems, preparing it for integration with the power and propulsion element. This was physical hardware sitting in a building in the United States, being assembled. It was real. Then on March 24, 2026, the same week Artemis II was less than 2 weeks from launch, NASA announced it was halting work on the Gateway entirely. Not because the engineering failed, not because a component didn't work, because the strategy changed. The official reasoning, stripped to its core, was that building an orbital station before establishing a surface presence was the wrong sequence. It was adding a step that slowed everything down. The new direction: go directly to the surface, skip the orbital middleman, build the infrastructure where it actually matters. The total NASA had already spent on Gateway between 2019 and 2025, $4.4 billion. That number doesn't go away. That's money spent on hardware that now has to be repurposed or stored or redirected. The HAAO module sitting in Arizona, still there. The international partners who contributed under a specific architecture, ESA, JAXA, Canada, UAE, left in a situation where the program they signed on to no longer exists in the form they agreed to. ESA's Director General was on record in 2025 describing his agency studying what he called alternative scenarios. As of mid-2026, ESA had not publicly confirmed what happens to its modules. That question is genuinely unresolved. And then, in July 2026, 4 months after NASA canceled the Gateway, President Trump signed legislation called the One Big Beautiful Bill into law. One of its provisions allocates $2.6 billion through 2032 specifically for the completion of the Gateway space station. $750 million a year for fiscal years 2026, 2027, and 2028. So the law funds it. NASA canceled it. The hardware exists. The money exists. Nobody has publicly explained how those things coexist. That contradiction is just sitting there, unresolved, while the agency moves forward with something completely different. SE Section, $600 million and 3 companies. What NASA is moving forward with is the Moonbase program, and the scale of it, once you look at what's actually being planned, is unlike anything that's been formally committed to before. On June 30, 2026, NASA held a press conference at headquarters in Washington. NASA Administrator Jared Isaacman and Moonbase Program Manager Carlos Garcia Galan announced contracts totaling nearly $600 million to 3 private companies for Phase 1 lander missions. Astrobotic received $297.9 million, the largest share for 2 separate cargo deliveries. Firefly Aerospace got $144.2 million for 1 mission. Intuitive Machines received $148.3 million for 1 delivery. Each of these companies will use updated versions of lander designs they've already flown. That's intentional. NASA is prioritizing speed and proven hardware over novelty. The whole Phase 1 logic is land things, learn things, fail fast, fix fast, build the operational knowledge base for when humans arrive. Lori Glaze, NASA's Associate Administrator for Human Spaceflight, described what these awards represent. She said they demonstrate NASA's commitment to accelerating, her exact word, the effort to build a long-term presence on the lunar surface and to developing the skills needed to survive and operate there. Ryan Stephan, NASA's Acting Director for Cargo Landers, explained the operational choreography. When a lander comes down, the terrain vehicles stay approximately 2 kilometers away to protect against plume hazard. The lander's exhaust kicks up lunar regolith at high velocity, and that material can sandblast nearby equipment. Then the rovers drive in, retrieve the cargo, and begin their assigned operations. During crewed periods, they'll cover up to 10 kilometers from the landing zone. Over the total lifetime of the rover systems, the planned traverse distance across the South Pole region is around 400 kilometers. 400 kilometers of driving on the moon, mapped out, funded. Beginning this year, Garcia Galan described the eventual footprint of the full moon base as hundreds of square miles. Different systems, different assets spread across the terrain, all of it building toward what he called a permanent lunar presence. And Jared Isaacman, in a moment of candor that's actually kind of remarkable for a NASA press conference, said that for perhaps a decade after the base's initial establishment, it's going to be, in his exact word, a mess. Incomplete infrastructure. Systems under development. Not the clean renders. A construction site on the most hostile terrain humans have ever tried to build in. No atmosphere. Temperature swings of over 300 degrees between lunar day and night. 2-week-long days, 2-week-long nights, micrometeorite bombardment, radiation with no magnetic field protection. He called it a mess. That's honest, at least. The very first Moonbase mission, Moonbase 1, is targeted for no earlier than fall 2026. Blue Origin's Blue Moon, Mark 1, Endurance lander will carry it to the Shackleton connecting ridge, a high-elevation area that sits between multiple features near the South Pole, chosen because it has both sunlight access from the rim geometry and proximity to the shadowed crater regions below. The payloads on Moonbase 1 include instruments designed to study what happens when a heavy lander fires its engines close to the lunar surface during touchdown. This sounds technical, but the knowledge gap here is real. Nobody has landed a large cargo vehicle at the lunar South Pole before, and the behavior of the regolith there under that kind of plume interaction isn't well characterized. The data from that mission feeds directly into how every subsequent lander is designed to approach. Moonbase 2 follows, an astrobotic Griffin lander carrying over 500 kilograms of equipment, including a prototype rover from a company called Astrolab. The rover is called FLIP, Flexible Lunar Innovation Platform. It's a smaller test version of what could eventually become a full crewed lunar terrain vehicle. The results from FLIP's deployment directly inform whether Astrolab's full-size crewed rover gets selected for later missions. Moonbase 3, also targeting 2026, will fly on an Intuitive Machines lander and carry NASA's Lunar Vertex investigation alongside international payloads from the European Space Agency and South Korea's Korea Astronomy and Space Science Institute. That mission will study something called lunar swirls, strange magnetic anomalies on the surface that create unusual bright and dark patterns and aren't yet fully understood. The South Pole region has several of them, 3 missions. Same year, all within months of each other, and all headed to the same general region of the Moon. The same region China is also heading to. China's Chang'e 7 mission is targeting a launch in the second half of 2026. Some reports specifically cite November. Its landing target is the rim of Shackleton crater, the same geographic feature that underpins NASA's entire Moonbase location strategy. Chang'e 7 is not a small probe. It's a 5-component system: an orbiter, a relay satellite, a lander, a rover, and a hopper. A small flying probe specifically built to drop into the permanently shadowed regions of the crater interior where no wheeled vehicle can safely go. In total, 18 scientific instruments across those components. One of the primary mission objectives is direct, on-the-spot detection of water ice in the shadowed zones. The hopper is the key element for that. It can fly over terrain that's impossible to drive, land inside the shadow, and attempt direct measurements that no remote sensing satellite has been able to make from orbit. Norbert Schurghofer, a planetary scientist who focuses specifically on lunar volatiles and has been tracking both programs, made an assessment that deserves more attention than it received. He said Chang'e 7 is, in his view, destined to find water ice and make the first direct in-situ measurements of it on the Moon. And then he added, the Chinese will be ahead of everyone else by at least 1 year, but probably several years. That's a scientific assessment, not a political one. The timeline gap is real. If Chang'e 7 launches in November 2026 and the hopper successfully enters the crater interior and returns ice confirmation data, China will have definitive measurements of what's inside Shackleton before NASA has its first crewed mission anywhere near the South Pole. Phase 2 of the Moonbase program, the part where infrastructure actually starts going up and where resource extraction becomes a real consideration, doesn't begin until 2029 at the earliest. China's Chang'e 8 mission is also planned for 2029, and its objectives include demonstrating the ability to make construction materials from lunar soil, what researchers call in-situ resource utilization, literally manufacturing bricks from the ground you're standing on. 2 programs. Converging timeline. Same crater. No legal framework covering what happens when both nations are operating in the same location. The Artemis Accords, which govern how NASA's partner nations have agreed to approach lunar resource use, have been signed by 43 countries. China is not one of them. Russia is not one of them. The accords don't have enforcement mechanisms. Space law currently doesn't clearly assign any sovereign claim over resources on the Moon to anyone, and the Outer Space Treaty explicitly prohibits national territorial claims. So neither side can own Shackleton. But whoever builds working infrastructure there first is establishing facts on the ground that no treaty currently speaks to directly. Come back to that crater, Shackleton. -183 degrees on average, dropping to -185 at the floor. No sunlight in 3.6 billion years. Water ice probably distributed from the surface down to several meters into the regolith, formed in the early heavy bombardment period when the inner solar system was still being shaped by impacts on a scale that's hard to even imagine now. Sitting there, unchanged, through every geological era of Earth's history, through every civilization, every war, every rocket ever launched, waiting for something or someone to finally land inside it. In April 2026, 4 astronauts flew within 6,500 kilometers of the Moon's surface for the first time in more than 50 years. They took photographs. Christina Koch described craters that looked like pinprick holes in a lampshade. They flew over the far side, lost contact with Earth for 40 minutes, came back around, talked to the president, splashed down 10 days after launch. The record they broke for farthest distance traveled by humans, 695,000 miles total, had previously been held by the Apollo 13 crew in 1970. That mission, Artemis II, didn't land. It was a test flight, systems verification, proof that the hardware works. The actual landing is coming. When it does, the target is the South Pole. The specific site is near Shackleton, connecting Ridge. The thing they're going there to confirm and eventually use is the water ice that Watson, Murray, and Brown theorized about in 1961, that Clementine hinted at in the 90s, that the Lunar Reconnaissance Orbiter has been mapping from orbit for 17 years. And China's Hopper might be dropping into that crater's shadow in November of this year, making measurements neither program has been able to make yet. The race isn't to the moon. It wasn't really about planting a flag, not this time. It's about water. It's about fuel. It's about whoever establishes working infrastructure at Shackleton, first potentially controlling the resource that makes everything beyond the moon, Mars, the asteroids, deeper, logistically possible. $4.4 billion was spent on an orbital station that got cancelled. $600 million more was just committed to go straight to the surface instead. $30 billion is the projected total if this goes to completion. And the specific geological feature at the center of it all is a crater that was formed before complex life existed on Earth, that has never once been touched by sunlight, that has sat in absolute cold silence for 3.5 billion years. Whatever's at the bottom of Shackleton has been there through all of it. It's not going anywhere. The question is which flag gets planted closest to it first, and whether that even means anything when no law currently says it should. So if you've got a read on this one, whether NASA's pace is enough, whether China getting there first actually matters, whether anyone can even claim what's inside that crater, drop it below. Genuinely want to know what people are thinking.